Okay, so earlier this week, we were talking about electrical testing. And so we talked about resistance testing, and we talked about how I could test it directly by using an ohm meter. We went over how to use an ohm meter. We also talked about how I can use voltage to infer resistance by measuring the voltage drop. Another way I can infer resistance is by current testing. So obviously, if a circuit flows too much current, it has low resistance. So that can be a sign that I have a fault. On the other hand, if I have something that's not working or has high resistance, I'm going to flow less current. So I can use current to infer resistance of a circuit. I can use current to compare the same circuit under different events. Or I can use current to compare the resistance of different parallel circuits that all share a main power wire. And so I can also do that. So I might do that in the case of ignition coils or fuel injectors, because I can see if I have one that's bad or something that's out very quickly versus taking everything apart and testing every one. So current testing has its place. We're going to get introduced to some current testing in our next module when we're talking about charging systems and starting systems. And we're going to see how we use current to test a starter, and we use current for testing a charging system. And I'll also show you in a video that I did how I can actually use current while I'm doing a starter test, starter draw test. I can actually use current to tell if all of my cylinders have the same compression or not on the engine. So here I'm going to test the starter, but show you at the same time, I can actually do what's called a relative compression test, which tells me are all the cylinders the same, which is obviously much quicker than the old mechanical way of getting a compression gauge out and testing all the cylinders individually. So current allows us to really get some neat information and some high level information, but it's only one of the tests we use. We don't use it exclusively. Because there's things that it's not going to show us, but we use it to complement our other tests. So there's two different ways that I can measure current with a meter or a scope. One is by directly placing the amp meter or amp meter function of the DVOM inside the current path. So it actually becomes a conductor and measures the amount of current flowing through it. Now that has some limitations. Normally about 10 amps is the most I can do that with. Anything more than that, I blow the internal fuse. Depending on the type of meter I'm using, that may be a cheap automotive fuse that's 50 cents or $1, or it may be an expensive meter fuse that's $15 to $25. So it can be an expensive, doggone it, I didn't mean to do that. Indirectly, by measuring the strength of the flux lines around the circuit with a shunt or inductive probe. So we have three different kinds of inductive probes. I have a high amp probe that will measure normally up to a high of somewhere between 400 and 1,000 amps, depending on the model of the probe. I have a low amp probe that normally measures up to about 60 amps, 40 or 60 amps, depending on design. And then we have a milliamp probe. And a milliamp probe is designed to measure current flow really under an amp. So it's very, very sensitive. So it doesn't have a lot of range. It's only going to read a couple of amps max. Very sensitive, and they're fairly expensive. So I actually don't own a milliamp probe because the price hasn't dropped on them yet. And I just refuse to spend $500 for one, especially since I'm not in the shop anymore. So for milliamp testing, I go directly and I put the meter in line because that's how I get the accuracy. If I am measuring amps, especially large amps, I'm going to be using an inductive clamp. So depending on the test I'm trying to do and the circuit I'm trying to test is going to determine my toolage that I'm going to be using. So if I'm going to current test using a meter or a scope, I'm going to set my meter to either amps, milliamps, microamps. I mean, how small amps we want to look at. And we can see here on my meter, I have a common, which is where the negative lead's going to go. This is my volt and ohm, where the red lead would go. When I want to measure amps, I would take the red lead out of here, and I would put it over here in the 10 amp socket. And now we're flowing current directly through the machine. So there's a wire that connects the common to the amp, and it just goes through that fuse. So there's no load there. If I'm going between common and volts or common by ohms, the meter is either the power supply or the load. They're insulated from each other. So if I, even no matter where I turn this dial, if I leave my wire here and my other wire is on common and I hook up on either side of the load where I have battery positive on one side and battery positive on the negative side, I will blow the fuse in the meter. Just like I would if I just took a fuse and put it across the battery, it's going to blow. So one of the issues we have, and I've done this repeatedly, is I use it on amps and I leave the meter lead plugged in. The next time I use the meter, I go to volts, I forget to check the meter leads, and I blow the fuse. So what I do now is as soon as I'm done measuring amps, I take the meter lead out of the amps and put it back on the volts. Because I've made this mistake enough times that I've blown a lot of fuses. And if you're not paying attention, it's still easy to do. I've done this a lot, and I was doing some electrical work. I had to put a new electrical line in my kitchen, and I was checking resistance on something. Actually, I wanted to check voltage, and I still had the meter hooked up to amps, and I popped the fuse. And let me tell you, at 120 volts, it made some sparks and all that stuff because it was a 20 amp circuit, 10 amp fuse. I blew the fuse in the meter, but it definitely, everything popped quite a bit. And again, I just wasn't paying. It was early on a Saturday morning and I wasn't paying as close attention as I should have been. So things do happen when we do so you are going to blow fuses in the meter. The Fluke meter that we see here is a very good meter. It's a fairly expensive meter, and the fuses are very expensive. Other meters, like my Vantage, which is a graphene multimeter and has a lab scope built in, uses a regular plastic automotive fuse that I get for 20 cents each. They're both 10 amp fuses. So needless to say, I like using my Vantage for doing testing more than I like using my Fluke because the fuse is cheaper. It's more tolerant of my mistakes. And sure enough, that's what I blew the fuse in, was my old Vantage. So that's the precautions and amperage. Now, if I'm going to use an inductive clamp, I'm not going to use the amp setting on the meter. I'm going to use the volt setting on the meter. So I'm going to plug my amp meter into the common and the volts, unless you're using something very specific that tells you to do it different. But you're going to plug it into common and volts, which is how everyone I've ever seen works. And here is my amp clamp. This one happens to be a 60 amp clamp. This is the same model we have at the campus. And so I have off, and then I have 1 millivolt equals 10 milliamps, or 1 millivolt equals 100 milliamps. So I get to choose my scale. So I'm going to read on my meter or my scope volts, in this case millivolts. And this is my conversion to amps right here. The neat thing about this is this allows me to use this on any meter, on any scope, because I have the conversion factor. All I got to know is when I set the scale and I'm looking at millivolts, hey, each millivolt is 10 milliamps, or each millivolt is 100 milliamps. How do I want to see the scale? And then I can figure out how many amps the circuit is drawing. So you can see where this is, nice. These are about $100. And they allow me to work with anything. If I get one like from Snap-on that I can use the amp scale on my meter because it knows that, and I tell it, hey, I'm using this probe set on this, and automatically now it's going to display amps. It's a $300 probe. It's going to give me the same information. One, I have to do math. The other one is made just for my Snap-on that'll allow the tool to do the calculation for me and give me a real amp reading on the screen. So for $200, I can do a lot of math. And we do have both at the campus. I just ordered some more of each because I think it's important to see that we're getting the same thing. One is I'm doing math, the other, but that way we can see the signal's the same. So I ordered some of each. So what is the maximum amperage that can be tested through a meter before the fuse may blow?
10 amps.
10 amps. Do you think that I think this is important to know? I see Ricardo's head shaking up and down because he's already taken all my tests. Absolutely it is. To me, that's something that you need to know. That saves your equipment. It decides how I'm going to test anything more than 10 amps, or if I think I'm going to go over 10 amps, I should be using an inductive probe. So here is direct testing with an amp meter. So if we look at my circuit, I start at positive. I come up through here. We've taken the fuse out. Now I'm coming up through a fuse holder, and that's just because we put one in there. I make some of these for the campus. And then it comes over to my meter lead, comes in my meter across here where there's another 10 amp fuse in here, comes down through the injector, through the PCM to ground. So you can see I'm in series with the circuit. So as soon as a fuse blows, as soon as anything happens, the circuit's open. So there's no protection for the meter. It is just a conductor. My only load is the injector. Everything else is power supply and conductors. So in this case, the meter is simply a conductor, but it's only allowed to conduct up to 10 amps. So an amp meter must be connected to the circuit being tested in which of the following ways. How am I hooking that amp meter up to make it work? In series or in parallel?
Parallel.
Series. Right? I'm in the series of the circuit, right? I started from here, because if I unplug the meter right here, is the injector going to work? No, because I'd have an open circuit. So the fact that current is flowing through the meter means the meter is hooked up in series. So we test for voltage in parallel, right? I'm measuring two parts of a complete circuit and measuring the voltage difference. So I'm measuring in parallel. Here, I've put the meter in as part of the circuit, so I'm measuring in series. Here is a mistake that a lot of people make. They take the load out of the circuit and then put the meter in place of the load. And what happens? I have a very sad meter because now there's no load. All I have is power supply and conductors. So I've got the power supply, comes through here, up, used to go through here, come down through here, all the way over to here. There's no load in the circuit. If there's no load and we apply power, what's going to happen? We start melting things. And that's why my meter is sad. It's having a bad day. Here is an example of an incorrect measurement that people do. Here, I'm measuring amperage by connecting the meter in parallel. So what I've done is I've now created two paths of current flow. I've created a parallel circuit. I have one circuit that goes through the fuse. I have another circuit that goes through the meter. So now I have parallel circuits. So my meter is not going to give me an accurate reading of what the current flow is. Now, I did have a really smart student a year or two ago. He goes, well, wait a minute, Mr. Bryan. If the resistance of the fuse is the same as the resistance of the meter, wouldn't it show half of what's being used? Applying what he learned in parallel circuits. And I said, yep, you would be absolutely right. It would be exactly half. But do we know that the resistance of that fuse and the connection is the same as the meter? No, we don't. But you're right, theoretically. He took it. He understood what we talked about by parallel circuits, and he goes, whoa, wait a minute, Mr. Bryan. Couldn't I just hook it up like this and figure out that what I see is half if the resistance is the same? And you're right. From Ohm's law, it would be half if the resistance is the same. The problem is we don't know the resistance would be the same, and I'm trying to get information for testing, and I need to know I'm correct. But in theory, yeah. So I love it when students bring stuff up like that because that tells me they're taking what we've already learned and applying it to something new we're learning and asking questions. So here's an amp meter connection. Here we've disconnected the load, in this case the injector. We've hooked an amp meter along one side. Now, does it matter whether my amp meter goes on the positive wire or the negative wire? No brave souls on a Thursday morning?
What was the question?
Does it matter whether I connect my amp meter on the positive wire or the negative wire?
Oh,
No.
No, it doesn't, because current flow is the same everywhere on the circuit, which means it's the same before the load and after the load. The only difference I'm going to get, whether I hook on the positive side or the negative side, is whether my amp meter is going to read positive amps or negative amps based on the location of the test lead. But amps is amps. It's going to be the same numerical number. So it doesn't matter which side I put it on, but I'll put it on the side that's the easiest. And that goes back to what? Our series circuit rule. Current flow is the same everywhere in the circuit. Therefore, I can measure it anywhere in the circuit. So it doesn't matter. So we went on the positive side here just because, but I could reverse it and use my jumper wire up here and put it on here. It doesn't matter. So we know that the circuit is using amperage, so the positive and negative really don't mean anything to me. The only time that the positive or negative mean anything to me on the amp meter is if I'm checking the charging system. Because I want to know that the alternator is putting current into the battery, not taking current from the battery. That's the only time that polarity is really important. When I'm checking the starter, for example, we know the starter is using the current. So whether my amp meter reads a positive or negative number based on how I have it hooked up really doesn't change the test result, because I know the starter is using the energy. I'm concerned with the number. How many amps is it using? So that's something to keep in mind. And I bring this up because that goes back to our series circuit rule. Current's the same everywhere. Therefore, I can test it anywhere on either side of the load. When testing for larger amounts of current, what type of probe should be used?
Inductive.
Inductive is correct, number 2. Not the comprehensive probe, although people have picked that one. I just made that one up. It sounded cool. Right? Who wouldn't want a comprehensive probe? It works on everything. Okay, so now we're going to do a little bit of tracing. So in the handout that I handed you, I want you to find the blower motor circuit. And here's my HVAC power. Here's my HVAC control assembly. So here's my blower switch. And I want you to draw the circuit with the blower switch in position M1. So if I rotate the switch from off to M1, and I'm now connected to M1, I want you to trace it all the way through my blower motor, which is over here, to 10. And I want you to show me where the constant power side is, the constant ground, and the switched power section is. So I'm going to give everyone a minute, to trace that out and look at this, and I'll show you what I came up with and explain it to you. And yes, the PowerPoint is in Canvas. I'll double check, make sure I'm not. I know it's there. I'm double check, make sure I didn't forget to turn it on. I'm pretty sure I did. Yeah, they're on. Ooh, maybe that one isn't. Okay, let me click that. It is now, Cynthia.
Okay, thank you. I didn't see that.
Under Chapter 52 meter usage circuit diagnosis is where this PowerPoint is. I'm sorry. It should be there. There's 2 PowerPoints. One is the book's PowerPoint. The other one's the one I use. Yep, and the top one is my PowerPoint presentation. There we go. Sorry about that. Checking which version I have here. I got a lot of notes in here for you. And make sure it's current. Well, the color sure got weird going into PDF, but yep, I got it all in there. Okay, cool. All right, so let's take a look at what I got and see how it compares to what you got. So here's what I have for M1. I have my constant power coming through my fuse all the way to the end of my switch. I have my switched power coming from here throughout my module through a wire down to my blower motor resistor assembly and through one resistor, the next resistor, the next resistor, through the normally closed contact in my relay, which would be pin 87A, through the switch in the relay in its default position, down to my blower motor, and then I have ground between my blower motor and G203. So hopefully this is what you got. So now, because I gave you guys several sheets, let's switch the motor position to M2 and highlight that page, and then M3 and highlight that page, and then high and highlight that page. So I'll give you a couple minutes to do the next 3 pages and we'll go over them.
Is it the red lead that's going to ground?
What do you mean is the red lead going to ground?
The red on the diagram. C circuit.
Okay, so the red right here is just my constant power.
Yeah, no, isn't it going directly to ground right after?
No, no, because this is my switched power. And it goes to my load, and then it's ground after my load. So this is my ground in green.
All right, so what are we doing with this?
Well, you guys, I sent you guys all copies of it, so you're going to be highlighting your M2, your M. You have a page that shows highlight M2, a page that says highlight M3, and a page that says highlight 5. So what you're going to do is you're going to rotate this switch to M2 and draw the circuit, to M3 and draw the circuit, and to high and draw the circuit. And I'll be right back to go over it with you. Okay, so let's take a look at
Sir
M2.
Brian,
Yes.
the M2 and the M3 goes the same path as the M1 except for the high. Can I cross the path of the high going to B9 connector to go to my load?
Well, the high doesn't go directly to your load. Your high has a
Yeah.
different load for that circuit,
Yeah, okay.
right? So I'll show you. So you're right. For the high circuit, the blower motor is no longer the load for that circuit,
Yeah. I
right?
was
What it's
thinking of
doing
that.
is it's what it's moving a switch in the relay, and then the blower mode is the load for the second circuit. So if we look at M1. You're right. It's almost the same. I mean, it's M2. It's almost the same as M1, except for we're not going through this resistor anymore. We're only going through
Yes.
this resistor
Yeah.
and this resistor. And M3, now I'm only going through
Yeah.
this resistor to the motor. So that's why when you put your blower motor on low, you're going through 1, 2, 3, 4 resistors. Each resistor is taking some of that voltage. So there's less voltage getting to the motor, less current flow because there's more resistance in the circuit. The motor goes slower. And then when I go to the next step, the motor goes a little faster. Next step goes a little faster. And that's why what we normally see with these is low speed stops working first, but the next 3 speeds work. Then the 2 low speeds stop working, but the 2 high speeds work. And eventually we get to only high speed works. And that's because the resistors in the blower motor resistor, the ones for low speed always melt down or burn up first. And so it's very common. We see this a lot in the shop where a customer will come in and complain that my low speed doesn't work on my blower for my air conditioning and heater, but all my other speeds work okay. And that's normally caused by a bad blower motor resistor because the low speeds burn out first. On the other hand, if speed number, say my M3 didn't work, but low M1 and M2 did, it couldn't be the resistor. It would have to be the switch, the wire, or the connector right here. But it couldn't be the resistor block because current had to flow through this resistor in the 3 other speeds. So if this resistor was bad, none of the speeds would work. So you see how looking at the circuit, drawing out how it works in the different things, and then figuring, okay, it works here and it works here. If it works here, all the parts that work have to be good. So if over here, all the parts that were good in the first place still have to be good over here where it doesn't work. So I need to concentrate on the parts that are different. And that's that compare and eliminate we were kind of looking at with the lights on the car. And as Cynthia noticed in high, I now change my load. So this circuit, I have power, switched power, my load, and ground. Now that I go to high, I've got my power, my switched power, my load, and ground. Well, wait a minute, the blower motor, I didn't go through it. So I need to look at this load and see this load, and this little dashed line shows that when I energize this and create electromagnetic field, we're going to move this switch. So this switch moves over to this position, which allows power to come from this fuse all the way down through the blower motor and here. So if all the speeds worked but high, I might want to go check this fuse because we know the blower motor works. So my only possibilities are I could have a bad switch, it's always possible, could have a bad relay, or I could have a blown fuse. So now it's down to what's easiest to check. Is it easier to check the fuse, check the relay, or take the dash apart and check the HVAC control assembly? Well, I'm guessing number 3 is not the best option. So now I'm down to, is it easier for me to test the relay, or is it easier for me to test the fuse? And many times the relay is easier. So I'll just check to see, is there power here? If there's no power here, then I know I need to go to the fuse. If there is power here, the question is, am I getting power here when I go to high? I am. So if I get power here and get power here, I have ground here, but I don't get any power here. It has to be what? A bad relay. So you can see where relays make great test points because in this example here, I I can isolate all 4 legs of the circuit at one test point, which means I only need to look up one thing, only need to find one thing, I only need to do all my tests at one location to figure out what direction my problem is, or if the relay itself's the problem, and relays go bad all the time. So that's why I say relays make great test points.
So Brian,
Yeah.
so it is the high that activates the relay. The other M1, M2, M3 goes directly.
Right,
to the
exactly.
relay.
Yep. So the low M1, M2, and M3 don't use a relay. They power it directly through the switch. But for high, we use a relay. And one reason for that is if we look here, this is a 20 amp fuse. This is a 30 amp fuse. So if I wanted to run a 30 amp fuse here, which like some manufacturers do, I would need to build a much bigger switch and use bigger wires. So since this is a module HVAC control assembly, I want to what? Let's keep it small. Let's keep it where it's not handling too much of a load. And then once we get to a certain point where you just have to work too hard, we're going to shift that off to the relay to do that heavy work. And because it's cheaper for me to manufacture the car and put this relay in than it is to build a heavier switch here, because I don't need that heavy switch for these 4 other settings. So I'd be spending more money where I don't need to do it. So that's, so manufacturers make those decisions. This by no means is everybody have a separate circuit for high. Some of them run them all through the switch. This rotary switch design is very common. This resistor block is very common. So these are pretty universal, whether I'm working on a Toyota or a GM like I am here. So pretty much no matter what car I have or how old it is, it works on this principle between the switch and the resistor block. So this is kind of a universal concept. So if I back up a little bit, and I have now battery power. I'm setting battery power down here. I've just connected the switch. So now I put battery power on here. What would my voltage be at pin C? Well, let me ask this. Have I used any battery voltage between here and pin C?
No.
No. So it should all be there, right?
Yes.
Okay. So I should have system voltage at pin C. As we go through a resistor, I should have less than system voltage at pin A. Then I go through another resistor, so I'd have even less voltage at pin D. And how much that is depends on what my applied voltage is. I have the value of the resistors. We could do some math, make our heads hurt, and I could confuse you further, but that's not the point. The point is that I'm going to have system voltage here. I'm going to have less here. I'm going to have even less here because as I go through the resistors, I'm using up some voltage. And really for testing, that's all I need to know. I don't need to do the math to figure out if it's working or not, because obviously if the resistor was bad and welded together or the resistor was gone, I'd have the same voltage at C and A, and that would tell me that the resistor's gone. It's welded past it or whatever. Now, my question is, and the hard question is that you need to think about for a minute, what does pin B read? How many volts am I going to have at pin B with this in the circuit? And I don't mean exact volts. I mean, am I going to have system voltage or less than system voltage or more than system voltage? What am I going to have there? I'll give you 3 choices. I'm not even asking for hard
voltage.
System voltage? Why would I have system voltage there?
There's no load.
Okay, well, you're half right. Actually, you're 2/3 right. So I would have system voltage at B. There is a load here, right? Because if I come from here back this way, there is a load. However, because it goes to an open circuit and there's no current flow, we won't drop any voltage around the load. That's why I said you're about 2/3 of the way there, which is great. So you're right. We'd have system voltage there because I can't use any voltage through here because I effectively don't have a load there because it's not a complete circuit. And this is the reason why I bring this up is people get confused a lot when they're testing this. Gee, I turned it to B and I got battery powered B and less than battery power over here. But then when I go to C, these both have battery power. When I go to A, all three of these have battery power. If I go to D, all four have battery power. I think the switch is shorted. Because people don't understand that even though I'm moving my switch, we have these open circuits where battery voltage potential is going to be able to be seen back on the back side of that. And this is what makes electricity confusing for people when they're trying to fix it. It's like, why do I have power at all four places when I'm on low? And they know the power comes from the switch, so the next thing you know, the car gets a new switch. Well, wait a minute. All we have is voltage potential coming from here back through a load on an open parallel circuit. Tim, did you have a question?
Was just going to agree with you that this is confusing. I'm not following this last part here about how there's system voltage there.
Okay, I'll try to go over it again because this is real important, and that's why I'm spending a little time on it. And you're right, it is confusing, and it's confusing to probably over half the techs that are working on cars today in the shop, which is why people buy things they don't need. This is a real important concept. So I'll move this to here. So now I've got battery power coming down here. My battery power is coming all the way over to here, and it hits its first load. It's going to drop some voltage, get to here, drop some more voltage between D and E, and then come down to work my blower motor. But I would still see full battery voltage or system voltage at C and B because the power is going to come down here. It's going to backfeed through here, through this resistor. Back and through this resistor. And from C, it's going to go up to G all the way over to where the little bullet point is for M1 that's not connected to anything. It's an open parallel circuit. So therefore, I'm applying voltage here. It's going to go through this resistor all the way over to here and stop. So there's no current flow. I can't drop voltage through a resistor unless I have current flow. So I would have all the voltage I started with as far as voltage potential. We're not doing anything with it. The same thing would be true with the next leg right here. Even though it's a 1.57 ohm resistor, up to B, I'm going to come up here through H all the way over to low. But since low is not connected to anything, it's just an open wire. So it'd be like if I took a battery and it's hooked up to my car, and that's my power supply. Then I take another wire to a light bulb, connect the light bulb to the positive side of the battery. The ground side of the light bulb isn't touching anything. And then I go and check the voltage at that wire. I would see all my battery voltage because it's gone up the wire, through the light bulb, up and stopped. So I'd see all that battery voltage at the end of that wire. Same thing's happening here.
Brian.
Yes.
So the only power source is where the switch is connected.
Right,
That's
exactly.
why there's no power on the rest of these figures.
You're correct. So on the rotary switch, the only place power is going through is where the switch is touching, in this case, M2. So all these other ones aren't touching anything. They're just there. So they're an open circuit.
Okay, I got it now. Because
Perfect.
the ground right there, they only get power because it is connected where the the wires are. But when it
Exactly.
goes up, because it's not connected to the switch, that means there's no power.
Right. So the power that we see there is actually coming through this way, but it's not connected. So it's just potential. It's like putting a wire onto a battery and not connecting it to anything. We'd see power in the wire, but it's not connected to anything. So it's not being used. Does that help with the explanation a little bit, Tim?
Excuse me.
I see some smoke there.
Yeah, it's coming out both ears. It does help. It's just that for some reason this is something I've never thought of before. So this is new. Yeah.
And this is huge because this is why people really struggle diagnosing electrical problems is that we backfeed on parallel non-connected circuits and we see voltage places that confuses us. So what you might want to do if you're struggling with the concept, and if you have a voltmeter and you have any kind of light bulb load, anything, is put one wire to the positive battery cable, then have it, and then not connect the other end, and take your meter and see the voltage there, and you'll see what I mean. And then you could take that same thing and connect it to negative, and you see you no longer have voltage there because now the bulb would use all the voltage. So it's the same time. It's just a continuation on the voltage drop exercises we did yesterday, but now I'm putting it into a circuit. Where yesterday on Tuesday when we were putting the numbers, we were okay, we're not dropping voltage because the switch is open, right? Or we're dropping all of our voltage across the switch where we have potential on either side. And here, all we're doing is we're seeing that potential. The issue we have is our digital multimeters have 10 mega ohms impedance. So even though we're hooking them in parallel here, which would make a parallel circuit, they don't flow any current. So I'm still going to see that voltage potential there. And that's what really confuses. So people think they have shorted switches. People think they have shorted wires, all kinds of stuff, because they're not understanding this concept that power is going to feed back in an open parallel circuit. So I think I've already made everyone's head explode. It's not even 9 o'clock yet. I'm trying to make up for yesterday. I didn't get to make everyone's head hurt yesterday, so we're going to work on it today. So we also have circuits that the question is it a series circuit or a parallel circuit? And it gets kind of confusing. So here I can see I have 2 cooling fan motors and I have 3 relays. So if I start, so I can figure this out a couple different ways. There's not one right way to do it. I can start at the load, and I know my load has to have 1 power and 1 ground to work, right? I can start at the power and trace my way down and see kind of where power goes or how many different places it can go. So there's not one right answer. And oftentimes, as schematics are confusing, we might need to start at different places and see where things come together. So if I start here with the load, which I often find is the easiest to understand a circuit. If I go up, okay, power comes through a relay, because here's the fuse. Here's a relay. So when this relay is closed, this fan gets power, which means the other side has to connect to ground. Because if it doesn't, the fan can't ever work. So the question is, how do we get ground? So if I come down through here, and I see here, so this is the default position, because that's how it's drawn. So I'll go with the default position first, and I come down through here, and then I'd have to what? Come through here to get to ground, which means that these 2 fans are in series currently. So if I put power through here, through the default position here, through this motor, up to here, into ground. So they're in series. What happens if I move this switch? Well, if I move this switch over, now I would come down power. I'm looking for ground, so we're going to go down this wire, and it goes straight to ground and doesn't power up the other fan motor. Which means that what? It's now getting a full 12 volts, not 6 volts, or it's not sharing its voltage. So that's my high speed. So the default position is low speed, and if I move this over, I get high speed. But how is this going to work if that's not getting power from over here? Well, if I come up to here, I have another relay. And so this goes to power. So this could come down. Here's power. Comes over, joins the ground wire, and goes to ground. So depending on the position of these 3 relays is going to determine, does just this fan come on? Does just this fan come on? Or do both fans come on? And several manufacturers control their cooling fans this way. So you can see where starting at the load kind of makes sense, because if I just started at power, if I tried to start here, I got power going to both of these. Both these are relays. Okay, so I close this relay. Okay, it powers up this fan. Got it. What does this one do? Well, this one also goes to this. So you can see, so there's not one place that you have to start. But if you get to a spot that you're confused at, go to another place. A lot of times I start at a load, and that way I can figure out, like in this case here, this load goes right to ground, which means this wire has to provide power. This side here, I can see it goes up to power. So that's power. This side has to be ground. So now from there, I can start figuring out so at least that way I know what I'm looking for on the other wire. And so oftentimes that's pretty helpful. And I think I included a copy of this schematic in the packet I gave you. So you can trace this or play with this. And so this is a series parallel circuit because it's a switchable circuit. And we do see these for daytime running lights and cooling fans. So here's a starter circuit. This one looks a little confusing. So when someone says, gee, my car doesn't start or my car doesn't crank over, what's wrong? Well, I don't know. How's the car built? Right? Because that's going to make a big difference. If I look here, I've got a battery. My battery goes up and see these dotted lines at the splice means this, this, and this are all the exact same splice. Same thing with up here. Where I go up here, I have this connector and this here, and this bar, which goes to this bar. So here and here are the same. So power comes around here. Power comes up through here to the generator. It comes over here to connect to these fuses. And it comes here to connect to the starter. So if I just go to the starter, I've got an open switch. Well, what closes the switch? Oh, some kind of contactor, relay, or solenoid. Okay, so I need to make this turn on. The ground for it is right here, which means it has to get power up here. So if I come up here, here's power. Oh, but it's an open switch. So this switch has to be closed by this load. Okay, so this load, one part goes to the computer. There's a switch that goes to ground. So the computer provides the ground. So let's see where power comes from. Power comes from, come over here. Oh, only if I am in park or neutral. So this is my neutral safety switch. I come up here, go over, come down. And oh, I have to be in the start position of the ignition switch. So this has to be pointed there. And then it gets power. So in order to start this vehicle, I have to have power come up, good fuses. Power comes down through here. Make sure I'm in park or neutral. Up to this relay, and then the computer decides if I can start the car. So then why would the computer be in charge? Well, a couple of reasons. One, maybe we don't want you stealing the car. Do you have the right key for this car? Do I like your key? That's one thing. The other thing is maybe we want the computer to control the starter. How many people have ever started a car and kept it on a little long and you get a horrible noise? Okay. Well, my computer on a modern vehicle has sensors that knows how fast the engine's going around. So if I'm cranking the engine at around 200 revolutions per minute, and all of a sudden I see that it is 300 revolutions a minute, does that mean I should turn off the starter now? Right? Because I'm going faster than what the starter can spin the engine. So even though my car is not at 800 RPM or 1,000 RPM yet, the computer already knows we started. So it can disengage the starter sooner, less drag on the engine, it's going to start quicker, the starter lasts longer. So the key point is not so much making the starter last longer, but it's lowering cold start emissions is why they do it. Almost everything on a car is about emissions. So they really don't care that your starter lasts for 400,000 miles instead of 40 like they used to. That's really not the manufacturer's goal. The manufacturer's goal, the reason why we have this technology, it really comes down to emissions, right? We want it to burn clean. We also don't want that car cranking any longer than necessary because cars are extremely dirty when they're cranking. They pollute a lot when they're cranking. So we want to limit that cranking time. Many new cars crank for a very, very short period of time. And then we can go from there into start-stop technology where the car is actually computers starting the car when you're in gear, when you go to accelerate from a stop sign. Whether you're working on a hybrid vehicle or a regular conventional gasoline powered vehicle. So you can see, gee, I turn the key and nothing happens is not as simple as what part should I guess at. I need to get a schematic and find out what controls it. Once I find out how it works, the next question is, where do I want to test it at? Is it easiest to test it here at the starter? Because if I have good battery power at the starter and I get a good signal at the starter solenoid, guess what? My starter's bad. I'm done testing. Maybe the starter's hard to get to. So maybe the starter relay is the easiest place to test it at. Because I'd be willing to bet getting to my neutral safety switch or my ignition switch is not the easiest thing to get to. My starter relay, on the other hand, is extremely easy to get to. Much easier than getting to the starter motor itself in many cases. As a matter of fact, some starter motors are buried under intake manifolds. They're 6 hours to get to, so it's not a good test point. But isn't a relay a great test point? So I could apply power at pin 87 and see if the starter works. I could see if I have power at pin 30. Does the computer provide ground here? Is the computer trying to make it start? Are we getting power here from my neutral safety switch and from my ignition switch? If I'm not, could I move my shifter to see if I get power? Maybe it's out of adjustment. So you see why that relay is, I mean, it's easy to get to, and it divides the circuit into 4 different sections very quickly and allows me to test those sections very quickly. So you can see why I really like relays, is because it is just such a great test point. So I'm going to introduce you to probably the most complicated schematic you're ever going to get on a vehicle. And that is power windows. And what makes power windows so hard is that we're switching both the power and the ground, and we're doing them at the same time. Because a DC motor goes one way up, I'm just using up, it could be down. If I put power here and ground here, my window goes up. But if I put power here and ground here, my window's going to go down. So a DC motor reverses direction based on polarity. So in order for a window switch to work, I can't just switch power on and off. I have to change positions. Hey, your power and your ground. No, wait a minute, your power and your ground, depending on whether I want to go up and down. So we have double pole switches. We got to switch both at the same time. To complicate that, don't we have a switch on our driver's door and then also a switch on our passenger's door or our rear doors, and they both work the window?
Yes.
So now you see where things get complicated. So, and we don't run them in parallel, we actually run them in series. So that means the default position for one has to allow the signal for the other to be passed through. So as we look here, and I sent you guys a copy of this, and this is not something I'm going to test you on, but I just kind of want to get you guys thinking a little bit here. So I can see here, I have my motor. My motor comes up to a switch. Make it big enough so I can see it. And the switch is inside a computer. In this case, the General Electric module. Great. And then I have an auxiliary relay up here. So I have a relay that's going to feed some power, and I got a switch over here. And so this right here goes in. If I look here, I have A and B here. I have C and D here. And this page, to be honest, doesn't make much sense. So now, because I'm looking at the motor, I'm looking at a computer, turning it on. I see this one-touch window thing, auxiliary relay. But I have this A, B, C, and D. That tells me it goes to another page. So I'm going to go to the next page, and I'm going to find my A, B, C, and D. So I've got A up here, B here, C, and D here. And it tells me what diagram to go see those at or where they're from. So if I look at A comes down, has a splice, and it goes what? Into the center here. It also comes over to the center here. Okay. Well, what is on the outside? Well, I have ground here. So ground comes up and it's on the outside here, 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 and here, which means A has to be what? Battery power. Okay, because I got two things. I got power and ground. And if you notice how the switch moves, so the switch is going to move. These are joined. So when this moves this way, it's touching ground here and power here. If it moves this way, it's touching power here and ground here. So you see how that's, right? You got this thing going on, right? So am I touching these? Am I touching these? Is what it's doing. Kind of ingenious, actually. And I'm reversing direction. So my two center ones are power. My two outer ones are ground. So I'm changing direction on the switch. And we can see this comes directly down to another switch. Oh no! But we're what? If I look here with B, B comes down what to the center. What's my outside? My outside is the default position, which is either ground, because this is defaulted to ground, or it's going to be wherever I switch this to. So as I switch this, now I'm able to change the direction through this motor. And so you could, this is as complicated as a wiring schematic gets. So if you're able to follow this at all on what I just talked about, everything else is going to see easy. Because here we're switching power and ground. And I bring this up because this really confuses technicians when they try to fix a power window, and power windows go bad all the time. So that is something that we do see and deal with. But it is really interesting how we're able to pass through the small window from the master from the small switch from the master switch because of how we default the position. And yet we can change it at the switch. So it's really kind of cool how they did this. They've been doing this for 50 years. So, you know, different manufacturers are going to draw their schematics slightly differently, but this is what they're doing. So I wanted
Sir Brian?
Yes.
So there is a switch in number 2 to make it turn right or left. Is that correct?
Well, it's not right or left. It's up or down.
Up or down? Okay.
Yeah. So the window's going up or down, or are you talking about the little switch that's not going right or left?
Okay. Yeah. So it's connected to the power, and then there's a ground.
Right.
That the outside kind of. Okay.
Yeah. So it's always connected to power, and when we move the switch, we're going to make either this side touch power, or we're going to make this side touch power, and the other side stays connected to ground. And since both these are the same as what this is, we can change. But if I'm not using this switch, then this switch has the ability to put power here or power here. So it changed that. So it changes direction to complete the circuit. So
why are there two switches?
Yeah. So this is the master switch on the driver's door. This is the switch on the passenger door or the rear door.
The passenger door. Okay, I got it. Okay.
Yeah. And I can see we're using a lot of smoke today, Tim. Which is good. I love this part.
Mr. Brian.
Yes.
I'm thinking about the door window of the car because I'm trying to like analyze how the door window look like in this diagram. Is that the two button? Is that the where you press it goes up and down?
Yep, that's the little rocker switch. So that little rocker switch for up and down.
Okay, I got it now because I'm trying to
right.
analyze.
So your little rocker switch is in the middle. So one way it connects here, or it moves this to here, I should say. The other way it moves this to here. So which way are you rocking it? You're pushing that. You're going to touch here, or you're going to touch here. Which way are you going to touch?
Okay. Now the diagram makes sense to me now.
Yeah. So we took a confusing diagram on the other page. Here's where really we're going to be doing our diagnosis, because everything from here just goes back to modules or other smart things. But this is where my switches are at. So this allows me to. So I just have that rocker. Am I going to touch positive here or touch positive here? And that's why when we're testing them, it's important to realize that, because you can see how easy it'd be to get turned around. Why do I have ground everywhere? Well, no one's putting power. Why just put power here and it blew my fuse, blew my circuit breaker, blew whatever? Well, because you got to disconnect it because it's connected to ground. You didn't disconnect it from ground before you gave it power. See, that's why when we test windows, we unplug them and completely isolate them and then apply power and ground. Or I have to test the switch and figure which side of the switch is broken. Is it the power side or the ground side? hit the switch and give it what it's missing. So these are a little more difficult to diagnose as far as because of how they feed the circuit. And so you see why I got a power window trainer, Ricardo. Because this was real hard to do on campus because, students, first of all, door panels only come on and off so many times. And then trying to do this on a live car between access and understand schematic made it really, really hard. But this is the schematic. And basically it's a double pole. We're switching. I got ground in both places. If I move this, I'm going to touch power here. Now I'm no longer connected to ground, so I'm going to be connected to power. Or here I'd be no longer connected to ground, so I connect to power. So depending on how I rocker that switch, I'm just moving that one or the other. And your head hurts. It's not even 9 o'clock yet. Okay, so let's have a little fun. Here is a 03 Explorer, and I apologize. You used to have a video of this, and I misplaced it. So crazy exterior lighting observations. When the brake lights are applied, the brakes lights work okay. My front park lamps, license plate lights, and both come on. The odometer and clock dim when I put on the brakes. With the right turn signals on, the right turn signals work, but my left park lamps and turn signals all flash, and my license plate lights flash. My clock and odometer go dim every time the lights on the outside of the car go bright. If I turn on my hazard lights, all the lights work normally, but my license plate lights also flash. My odometer and clock dim when my lights flash on the outside. My left turn signals work normally. When I turn on my headlamps, all my brake lights come on, but my headlights and park lamps work normally. So obviously we have something shorted here, right? And if I'm looking at definitions, I have 4 possibilities. I can have an open circuit, a high resistance in a circuit, a short to power, or short to ground. Well, it can't be high resistance, and it can't be an open. That leaves us with what? Short to power or short to ground. And since multiple systems are being affected, and by what we call parallel control, where I turn on this and this over here turns on, that is almost always a short to power. So if it's a short to power, I need to analyze this and figure out what can't be wrong and what could be wrong just by thought, and then compare the wiring schematic. So what I'm going to do is I'm going to take the wiring schematic for this vehicle, and what I've done is I've highlighted in red each of the different operations. So here I have my brake lamp operation. I've got power coming through to my brake light switch. And then it goes through what's called my combo switch, which is your turn signal switch on the steering column. Then it comes down to my left rear brake light and my right rear brake light. And here's my high mounted or my third brake light. So that is what my brake light circuit works like. Now, if I look at my right turn signal, I get power from a different place. I come through my combination switch, and now we've moved that position of the switch. And I'm going to come down and I have a turn signal indicator, and I have a rear turn signal bulb and a front turn signal bulb that I'm using. If I turn on my hazard lights, I've moved the switch here again, same power source, changed the position of the combo switch, but now I'm feeding power to both indicators on the dash, and both front lights and both rear lights. If I turn on my headlights, now I get power from a third source. I come through a headlight switch. And then from here, I'm going to come down and I'm going to power up both my license plate lights, both my rear lights, and both my front lights. So based on what we've seen, is it possible that my headlight switch is the problem?
Probably.
Well, think about this. Do I use the headlight switch for all of these functions or only for headlights?
For headlights.
Right. So whatever is shorted has to be something that I use for all of these functions.
Oh, okay.
Right? Because I'm not going to jump from my rear brake light up to my headlight switch. It has to be something that everything goes through. And since I only use my headlight switch for headlights, it can't be my headlight switch. Okay? Just like, remember, my left turn signals don't work. Work fine. So it can't be my left turn signal bulbs, right? Because I don't have a problem when I use my left turn signal, only when I use my right. So if I back up a little bit here, so here I have power coming through here, and I have the combo switch, but in the previous light for my headlights, I don't use the combo switch, and I know I have the problem when I turn the headlights on. Therefore, it's probably not the combo switch because I don't use the combo switch when I use my headlights.
Go ahead.
Are you kind of following the thought process here a little bit? So here's where we're going to kind of compare and figure out what is most likely not the problem, and then look at what we use in every one. So we don't use that there. So, and if I use the brake lights, oops, I'm sorry, that's right turn signal operation. Right turn signal operation, I'm only using the right turn signal. So if I go to left turn signal operation, I would only use these two bulbs. So it can't be these bulbs because I don't have a problem when I use those bulbs. I do have the problem with the brake lights, and yet with the brake lights, it can't be the brake light switch, and we've already seen the combo switch is unlikely. It can't be the left side brake light. How about the right side brake light? Do we use this for everything? Let's look. Do we? Am I going through the brake light bulb? There's two filaments, but am I going through that bulb every time? Keep an eye on it. I am, aren't I? I'm coming through this filament, going through this filament again, going through this filament a third time, and then for the headlights, I go through this filament. So this bulb and connector is the only part that is used by all four systems that are having a problem. Is it worth taking a look at that now? Is that easier to get to than taking the steering column apart, taking the dash apart? Again, I want to get the most information with the least amount of work. So far, I haven't worked real hard. I've looked and see how the car works. I've gone and pulled out a schematic, gotten my highlighter, and highlighted how the different circuits work to see if I could see a problem. Because I'm a visual person. I like to do that. And here's what we pulled out. So this is a bulb. And what happened, this is a dual filament bulb. So there's two circuits, one here and supposed to be one here. And what happened is the bulb broke, but this filament jumped over to this other post and welded itself on. So now they're shorted in the bulb. So this possessed car that's doing all these weird things needed a new bulb. So if I told you, man, I charge you $100 and I put a brake light bulb in, you'd go, whoa, $100 to put a brake light bulb in. But am I charging you the $100 to put the brake light bulb in, or am I charging you the money to figure out what's wrong with the car and use my skills? I'm charging you the money to use my skills, because a less skilled technician might be selling you that combo switch and you got a $600 bill. And then after he puts that in, he figures out he still has a problem. Then he eventually discovers the light bulb and doesn't charge you for it. But he's not taking the combo switch back out. I can guarantee that. So, you know, it's amazing how many times customers will be upset with a smaller bill, even though it's a fair bill, because you're able to diagnose it efficiently. And they're like, well, how much for what? Well, wait a minute. You wanted your car fixed. You should be happy it's less money, needed less parts. But somehow customers like, you charge me how much just to do what? I charge you that much to fix the car. You know, and some cars are easier than others. I've seen technicians spend a good part of the morning figuring this out and still not get there. So I see Cynthia's telling you how confusing it is, Ricardo.
Yes, it is.
Well, you see why Ricardo took my class twice. And he got an A the first time he took it. So, I mean, he obviously saw that, there's a lot of different things we can learn here.
Yeah, it's obviously practice, practice. You already know that, Brian. And I just want to say that because it is confusing, but you have to see it a couple times, and you have to practice it like anything else. And after a while, it just becomes second nature.
It is, and the practice we can do here, because we are online, is we practice it intellectually. So I use problems like this, and I'll come back to them as we talk about different systems. And then we get comfortable with what we know. And it's always amazing. We don't know what we know. What we know, we assume everyone knows many times. We don't realize what we've invested to learn what we know. And yet we've had to learn everything we know. There was a time when tying our shoelaces was impossible. It was too hard. Why won't you do it for me? I can't do this. Normally resulting in tears, sitting in the bottom of the stairs in my case, and I was about 3 or 4 years old. Because it was impossible. I didn't have that struggle this morning, I'm happy to say. I can now tie my shoelaces 5 decades later. But I think for a lot of us, things are that way. We don't think twice about what we know, but learning things is always hard. And yet when we learn them and we've invested that time, we don't give that any credit. We don't really, well, doesn't everyone know that? And no, not everyone does, but because we know it, and often we don't think of ourselves as really knowing much. We just kind of consider ourselves average, at least I do. It just, well, I mean, everyone doesn't know that. And no, not everyone does, because not everyone has had our same experience. Not everyone has learned. And that's why I learned something in every class from my students, because you all know things I don't know. And I'm smart enough to know that, or smart enough to know I'm dumb, one of the two. But it is. So as we go through these things, you're going to find, and I see this with every class, at the end of the class, students are telling me things that they had no concept of the first couple of weeks. And they're explaining them to me by week 10, or they're asking me questions based on week 10. And they don't even realize they know it. They're just doing it. And I will also tell you that the electrical module is the hardest module in the class. So we start off with the hard stuff, and then we can kind of ski down, right? If I'm hiking, I want to hike uphill in the morning and hike downhill in the afternoon. No one wants to hike downhill in the morning and then, gee, I'm tired and now we got to climb this thing. That's going the wrong way as far as I'm concerned, right? So I'd rather let's climb the mountain to begin with, and really do the hard work, and then get into spots where it doesn't feel as overwhelming. So the first module 1, because of what module 2, excuse me, because of what we're doing with electricity, I mean, going from 0 to 100 is really by far the hardest module. It's also, I think, the only module I have with 3 chapters in it. So it is by far the biggest and hardest module that I have. So testing tools. So this is a Power Probe. You guys have heard me talk about it a little bit. So Power Probe does a couple of different things that are unique to the Power Probe. One is it connects to the battery, and it has about 20 feet of lead. So I can go about anywhere on the car and I'm still connected to the battery, which means I have a good ground and a good power for it. A Power Probe 3 or 4 is going to have a voltmeter in it, so I can see what the voltage is where I'm testing. But believe it or not, I really don't use it for the voltmeter as much as I use it for the fact it has a red and a green LED in it, and it beeps, and it beeps a different sound whether it's on power or ground. And that beeping tells me that I don't just have voltage potential, but I actually have voltage I can do something with. So very quickly I can see, hey, I got 12 volts, but it's just voltage potential. I can't do anything with it. Or hey, I got 12 volts that's beeping at me and telling me it's ready to power up a light bulb. Or ground. Hey, I got a good ground here. The other thing it has is it has a rocker switch on it. And this rocker switch can be used to apply power or ground at its tip. It also has a separate lead hanging on the side of it that is a ground lead. So this allows me to connect it to here, connect the Power Probe to here, push the rocker switch to power, and watch the light bulb come up, or watch the window go up, or watch fill in the blank. So this is a portable power supply that's connected to the battery that gives me a 20-foot cable. If you buy, the bigger kit comes with a spare 20-foot cable. So if I'm working on my truck with the trailer on it, I can go all the way back and check my trailer lights. I'm still connected to the main battery. So I can see, do I have a bad ground in the trailer? I can troubleshoot the whole thing very efficiently. This is what's replaced test lights. So I use this much more than a digital multimeter, although it doesn't do all the same functions. It's a voltmeter. It doesn't do ohms, doesn't do amps. It doesn't take extra leads. But as far as troubleshooting, this is probably one of the number one tools in troubleshooting. The Power Probe 3 is very reasonably priced. You can get it in different kits with different adapters. I would highly recommend getting a Power Probe 3 if you plan on either making this career or doing a lot of stuff at home and serious hobby. This is bang for the buck. This is a huge tool. And you don't need to spend the money on the Power Probe 4. You can if you want, but the Power Probe 3 is more than sufficient. And it's just a great tool, and it has a built-in 20-amp circuit breaker. So if you hook up to a motor wrong, or you hook up to something wrong, and you try to power it up and it pops the circuit breaker, you go, whoa, I just popped the circuit breaker. What did I do wrong? You can look at it, push the button in, didn't cost you anything, and redo it. So this is great for bench testing stuff. It's great, we were doing that blower motor test. I can go out, I can use this to power up a blower motor. I can use it to power up solenoid. I can use it for all kinds of stuff. So this is, now if I don't use it right and understand the wiring schematic, and I put ground where there's supposed to be power, or power where there's supposed to be ground all the time, we can let the smoke out of something, or I can kick the breaker on the meter. And that's why it's important to know how to read wiring schematics before we just start applying power and ground places. But this is a great tool. We use these. I use this all the time. This is my number one. I got to go troubleshoot something electrical. This is the tool I'm grabbing. I don't care if it's a vehicle that doesn't start. There are some other companies that are making knockoffs. My recommendation is get a real Power Probe. They're not that much more. They hold up. I've had some of these for over 20 years. It's a one and done type of tool. I shouldn't say it. The early one, I have some Power Probe 2s, and the connectors weren't as big. So I used my first one so much, I melted the connector that connects to the longer lead. So I bought another one and just hardwired that one. So I still use it. That became my home Power Probe. And then I bought another one where now I got 60 feet of jumper wire. So I can really check a long trailer. Here's a homemade substitution box that we built. And this is kind of a fun project. And what this is 6 1157 light bulbs. And we hook this in place of a load on the circuit. So do I have enough power to power, my solenoid or power my window motor? Well, guess what? I can unplug the window motor, plug this in. If all 6 light bulbs light up nice and bright, that's 15 amps. That means my wiring connectors, everything else are doing good. So I use this also. If I want to test the power going to a module, I'll unplug the module before I replace the module, make sure I have good power and grounds. The big thing I use this for is if I'm blowing a fuse, I'll take the fuse out that keeps blowing. I'll put this in place of the fuse, and then make the light. If the light bulbs are on, I have a short. Then I just have to make the light bulbs go out to fix the car. That's a lot easier than keep putting fuses in. Because I understand the circuit works with power supply, conductors, and a load. Well, if the fuse is blowing, I'm missing my load. So let me take the fuse out, put a load in its place. And as soon as the load goes out, guess what? I now have an open circuit. I'm not going to blow the fuse. So, again, just different kind of tools. So this is 6 1157 bulb sockets in a project box. If someone's actually interested in building this, send me an email. I'll send you the couple pages of directions and part list on it. But I just have, like I said, a lot of this is about getting us to think. So here's an example of where we use this on a car, where I have battery power and ground. I have a fuse that keeps blowing because the wire is rubbed through and shorted before it gets to my load. So we took the fuse out, put the substitution box in its place. The light bulbs are all bright. As soon as I'm no longer touching ground here, the light bulbs are going to go out or get extremely dim. I've just found my problem. So this is great because I can wiggle wires. Are my light bulbs now getting dimmer? Are they flickering? Tells me that, oh, I'm on the wire that has the problem. So this is, again, it's a different way of diagnosing the problem. The book talks about using a resettable circuit breaker. I don't like resettable circuit breakers for a couple of reasons. One is I'm resetting the circuit breaker so it's going to pulse. So I'm going to get it's going to flow current, pop the circuit breaker, flow current, pop the circuit breaker. It's a little hard on the circuit breakers. It's hard on the wiring and the connectors, and I've actually melted wiring and connectors before I found the problem with doing this. Because you remember, we're hitting the maximum. How many times we're going to hammer something against the maximum before something else in the circuit gets unhappy? So it comes out of how long does it take to find it. And the other thing is, I'm looking, I don't really know when I found it. I don't know if I've got an intermittent problem. If I've wiggled the wire and made a change, I'm not going to know that using that resettable circuit breaker the way the book talks about. With this right here, I know instantly. So I've made a couple of these over the years. I've made them with this one's nice because it has the 6 light bulbs in it. I've also made one with just had 1 light bulb in it and a buzzer. And it was a air brake warning light buzzer is what it is. They're a light with a buzzer on them. We use them on semi trucks, anything with air brakes. And I put that into a kit box with a power and ground. And that was nice because I didn't have to see it. So I could hook it up and you'd hear the buzzing on something I hooked up underneath the hood or underneath the dash, and I could work in the trunk and still hear that. Now, it drove my coworkers nuts, and I wouldn't want to use it every time if I can see the bulbs. But that's another way of doing it. So there's lots of ways to get there. We also use different substitution tools and simulator tools. So here's a box that I can put in resistance into a circuit. I can put in frequency into a circuit or other signals to see if the circuit's able to carry a signal or is it shorted. There's different short circuit finding tools. This goes a little bit in the Wayback Machine. Use a little arrow needle, and based on where the current was flowing, the needle would go towards the current. So I'd go down this way to the short, and if I went past it, it would face the other way, and I could find the short. So again, that's 1960s technology, 1970s technology. Newer technology, PowerProbe makes a tool, which I have. Never had a lot of, I've had it fix a couple, I've had it help me fix a couple cars, but I don't use it very often. I've had it a long time. But it actually puts a signal on it, and then you find it where the open is, or you find where the short is, and it's putting a signal on the line. And I found that helpful when I don't have access. So for example, I found a broken wire inside a quarter panel of a Fiat that you couldn't get to without a lot of disassembly, but this let me know that's where the problem was, so I do need to disassemble it. So, you know, again, there's a lot of different levels. How often have I used it? I've owned the tool for probably 20 years. I've probably used it 10 times. Okay. Because it's not my go-to tool. We don't have shorts very often. We have opens are more common. Most opens are easily accessible. And I can find them quicker than getting the tool out. So even though I spent $150 on the tool, I don't use it that often. I don't keep the batteries in it because I don't want it to go bad, but occasionally it's gotten me out of some jams. So it's not something I'd recommend buying, but there is a lot of stuff out there. Back probing tools. So if I buy a voltmeter, it's going to come with a set of leads. So the inexpensive leads come and they just have a set of pointy leads on them. And if they're fancy, they may have some alligator clips that clip on the end. As we get more expensive leads, what we're going to have is we're going to have what are called banana plugs on each side. Banana plug is normally the plug that plugs into the meter, and the other side has banana plugs. And then I can put on a regular hand probe on the banana plug. I can put an alligator clip on the banana plug, or I can put these needle probes on the banana plug. So this is a set of probes that these plug onto the banana plugs, and these are literally needles that go in. And this is nice because it comes with a spare set of needles. So when you break them off, you can do it. And this is what we use for back probing. So, and I have, as we move on in the class, you'll see video of this, you'll see pictures of this. And what it allows me to do is go down the wire on the back side of the connector and insert this until I hit the metal. and then I can get a good signal. I never want to pierce wires if I can help it. What I want to do is back probe them by sliding down the back side of the connector until I make contact with the metal connector inside that housing. And so this is a tool we use for those. And this is the best one I found on the market. These are front probing tools. This is not the kit I like the most. This one's very reasonable. There's other kits I like better. But what these are is those banana plugs I was talking about. Now I can plug on something that's maybe a 64 thousandths diameter connector, or it's a 2 millimeter spade connector, or a 1 millimeter spade. So now I can go right into the connector. So I'm not taking this round thing and shoving it into a connector and damaging my connector. I'm taking something that's exactly made for that connector, plugging it in for a test point, or making a jumper harness for test points, or all those kinds of things. So those are one of the things we do. There's some solid core high current adapters. This right here, these are called amp probe adapters. So many times I might want to do a test at the fuse box, but the fuses are in the fuse box and getting to the wires on the backside are really hard. So what we do is we take the fuse out. I put the fuse in the side of the amp loop. Now all my current is still going through a fuse, but it's going through this loop of wire. Then I can put my inductive clamp on here and measure the current through the circuit. So I've just made a really easy test point. It's a lot better than digging wires out. These are one of my favorite tools. These are relay testers. And what these are is you take the relay out, you plug this in its place, and then the relay plugs into the top of it. And it gives you your terminals for the relay, and they're marked. So you heard me talk about pin 830 or pin 87 or whatever. They're actually numbered. So then I can do all my testing with my preferred tool, which happens to be a power probe, right here. So all I got to do is figure out what relay is for the circuit that's not working, take the relay out, plug this in, connect my power probe, and then I can test the whole circuit based on the wiring schematic and watch the relay that's installed in the top work and see what's going on with the circuit. And when we get into cooling systems, I do a demo on this and you'll get to see it. I have a video lab that we do. So there's 8 of these. The complete kit only comes with 8 of them. A set of pliers, some jumpers, and it's pretty reasonable. I think it's what Chris, you were just looking at, it was about $120, something like that, $130.
Yeah, they had a couple of different ones. One of them was like 125, and then the one that the Lyle one was like 150.
Okay, yeah, and the Lyle one is the one you want. It's in the gray box, comes with all the stuff. You see some other kits that come with fancy relay testers that they want to sell you that have LEDs. If you can read a wiring schematic and have a power probe, you don't need to buy a relay tester. Relay testers are for people that have no idea how anything works, so I can put it in and have the relay tester tell me. It's not going to help you fix the circuit. It's just going to tell you, is the relay good? Well, that's only part of what I want to know. So why don't I learn how to read a schematic and use tools? But these are awesome. I hate testing a car without these because it's a pain. These are such a time saver. Some of the best money I ever spent in the shop. Then you have different kind of shrouds, adapters, fuse jumper wires, homemade test harnesses. There's all kinds of things that we do for electricity. I have a whole drawer, actually drawers of just test leads and jumpers and things like that, but I do a lot of electrical testing. So like anything, one thing I'm convinced of, I have several hobbies that I like doing. And what I'm convinced of is every hobby I've ever found I like, I can spend more money on than I can possibly make. So I saw, this is cheap to get into. Oh, this is cool. And it doesn't take long to figure out the first stuff I bought really wasn't good stuff, even though it was the best stuff they sold at the first place I went to. Then you find there's better and better stuff. And you finally find it at a point to where, okay, I'm never going to get the best stuff because it's outpriced me. So I'm going to get to where I've got good stuff I like or whatever. But yeah, it's pretty amazing. And I don't care if you're talking toy trains or woodworking or cars or model airplanes or model race car, the remote control race cars. I don't care what it is. You can spend a stupid amount of money on any of it. And the question is, how much do I need to spend? What benefits me and what's valuable to me? And that's different for everyone in this room. And so I just want to emphasize that. I don't want anyone going, Brian says I need to spend all this money. No, I'm not saying that. I'm saying that if you're going to spend money and you're interested in this, these are tools that I have found a great return on investment on compared to other tools I've bought, and I've bought plenty of them, that the return on investment is horrible. They've never paid for themselves. But I bought them because it sounded good. Let's see if it works. And I'm willing to take that chance. And I've taken that chance to the point where I've had to have really big toolboxes, as you can see behind me, because I've bought a lot of tools, and some of them have really paid off, and some of them have not so much paid off. So if I've already learned that tools don't work good, why? I think as an instructor, I kind of try to help you not make the same mistake I did.
For you a minute.
So this is a great question. Could I use a tone generator probe one that a phone IT wiring techs use for tracing and opening? You could certainly use a tone generator, which is basically what the power probe's doing, the little kit that I saw, the expensive one. And then you're using that with the probe one. So that's basically the power probe tool that I was talking about. So yeah, that would work. And like I said, the automotive one's about $150. I'm sure there's some other stuff that's less expensive for tracing open. The advantage of the power probe one, it'll also help you trace the short. So it'll do shorts and opens. But yeah, absolutely. So that's another way of doing it. The issue we have with automobiles is many times things are not accessible. They disappear up underneath the dash. They disappear into a harness with a whole bunch of wires going through lots of pieces of metal insulation. So, the idea is not to disassemble things. That's why we really got to pay attention to where the connectors are, where the test points are, and so on. And one thing I did point, what is a drag and why do we need to check it for drag? I'm sorry. Let's see where I have drag testing tools. I meant to talk about that. So a drag testing tool. So here we have a connector, and a connector in this case has a lot of female pins. And what happens is the female pins open up, so I'm not getting a good connection. And this problem has gotten worse because the pins have gotten smaller. We're now down to 32 thousandths diameter pins. So the simple weight of a connector that someone didn't secure can be enough to damage the female portion of the pin connection. And once they get loose, now we don't make a good electrical connection. So what we're doing here is we're using a tool, which is a front probing tool of the correct size, to put into the female portion of the pin, and it should hold the weight of the connector. So when I insert it, it should have enough drag to hold the weight of the connector. So if I insert it, go up, and the connector falls off, the female pin in the connector is bad. That could be my whole problem with or intermittent problem with my wiring. And we see this a lot on newer vehicles. So one of the things we do is drag check connectors to make sure we have what's called good pin fit. We have a really positive connection. And this can happen for big connectors. It can happen for little connectors. It can happen for the connector, the diagnostic link connector you plug a scan tool in. Those connectors get worn out. It can be for the electric cooling fan. Gee, I got power and ground. I plug it in and it doesn't work. Well, voltage drop check proves it's the connector that's bad. So is there broken wires where it's soldered in the connector or crimped in the connector, or is the connector itself is too loose?
What is the meaning here? What is the meaning for gadgets?
Gadgets is little trick tools to help us fix cars.
Is any word meaning for the gadget or any special design?
No, gadget is a encompassing term where it means any type of, in this case, any type of accessory that might make it easier to test an electrical system.
Okay, thank you.
Is how we're using that here. So another thing I did put in here in this PowerPoint as a resource for you is based on how many amps the circuit is flowing and how long the wire is, what is the minimum wire size that would be acceptable. So many times manufacturers use a wire size larger than this, but this is the minimum. And this is for automotive 12 volt applications. So this is in the PowerPoint that's in Canvas. It's all part of a PDF. You can download it or whatever, but I just want to let you know I put this here as a resource for you. Okay, so I'm going to stop sharing this one. So quite a bit to electrical testing, isn't there?
Yes. Too much information, Sir Brian. My head hurts.
Oh, it's not too much. We'll get more in there. Trust me. I am confident.
It is reading through the complex wiring, and the identifications are so small. It's hard to like read it.
Well, they are small, and that's hard. Matter of fact, I was at the shop one day and I had it blown up as big as I could on my monitor because it printed out too small. I got my magnifying glass and I'm up on my monitor reading a wiring schematic on my magnifying glass. And my boss walked by and I had a 22-inch monitor at the time. 2 days later, I had a 32-inch monitor in my bay because my boss realized that I'm the guy who's fixing all the cars. I'm doing all the electrical diag. And as I've gotten older, during the time I worked for him, I went from not wearing glasses at all to bifocals. So he'd seen me that, and when I first got my first set of glasses, which were bifocals, I said, man, I didn't realize how bad my eyes were. He goes, I did. So apparently it was pretty plain that I was having issues. But so I was the only one in the shop that had this big monitor because I did so much wiring stuff, and because my eyesight, he realized that I just need to see this stuff. And then as things got worse, I had the magnifying glass on that monitor. Means it was time to go get new glasses.
I need to get a magnifying glass.
Yeah. So I print a lot of stuff out, use a magnifying glass. I use bigger monitors. There's a lot of stuff like that I use. But yeah, it is difficult. So why do I use difficult schematics in class? Because that's what you're going to use if you ever try to fix a car. So I'm a big believer in not sheltering and having everything's nice and simple. We feel great about it in class, and then you see your first real wiring schematic and you're terrified. Let's deal with some real wiring schematics and let's pick them apart and figure out they're not as intimidating as they try to be. At the same token, I use some big schematics to show a circuit or to show circuit test points. So I use both in the class, and that's why. But I really want to try to expose as much real world stuff that you go, whether it's on the weekend during this class or after class during the week or after you leave this class and you try to do something. I don't want you to pull something out and go, this looks nothing like what Mr. Brian taught me. So I'd rather expose you to it. So that's why I do that. I don't use those generally for tests because I do know they're hard to read. And tests are about theory. Do you understand the theory, not how big is your monitor and how good your eyesight? Because I have some students that have taken this whole class on an iPhone or on a cell phone. So you can, so I try to keep that in mind. But for the purpose of our discussion and demonstrations, I really try to expose you to the whole thing. So we're going to move into battery technology. And I'm going to start with it just a little bit. Oops. Because I should start it. There we go. So our next module, and I opened up the module already, is battery technology. So I have three things in module 3. I have battery technology, which is the heart of the electrical system, and then I have starting and charging. So in this module, we have a couple CDX chapters. We got a couple different PowerPoints. We also have some labs. And the labs in this chapter, and I'm going to open the labs up after I talk about them in lecture. I have a battery testing lab, a starter testing lab, and a charging system testing lab in here. And the labs are going to consist of you watching a video that I did and filling out the corresponding lab sheet and turning that lab sheet into me. So you don't have to have any special equipment at home, don't have to have any special tools at home, but I walk you through testing the battery, testing a starter, testing a charging system, walk you through the different steps I'm doing, walk you through the different tools I'm using, and then ask you questions about it on the lab sheet that you're going to fill out and send in to me. So this is the best I was able to come up with. Yeah, Chris, that's fine. This is the best I was able to come up with when we went virtual, when we went online. So I spent some time learning how to edit videos, buying a video camera, setting stuff up in my lab and creating some of these videos. So this was a whole new thing for me a year ago. And some are better than others because it's still a work in progress and I got a ton more I need to make the time to do. But that being said, so when you see a lab, don't get intimidated of I don't have anything, or I don't have a car, or I don't have a place to do it. You all have a place to do it. So most of the labs, actually all the required labs in this class, are things you can do with no tools at all. I do have some extra credit labs in this class that require high-tech tools like a tape measure or a yardstick, and turning headlights on and going out and doing a visual. And those are extra credit labs. Because I understand maybe you don't have a tape measure or a yardstick. That's fine. Maybe you're only going to do part of the lab. So I do, so extra credit labs, things that require tools, I usually put in as extra credit. So they're, if you want to do it and people normally do, and I enjoy them, that's great. If for some reason you can't do it or don't do it, it doesn't affect your grade. It doesn't hurt. It's just extra points and all. So battery technology. Is changing with the advent of hybrid electric vehicles. But at the same time, it really hasn't changed. And what I mean by that is we're changing the chemistry inside the battery, but how we put a battery together is really the same now as it was 100 years ago. We're really not changing how we get a car battery put together or a high voltage battery put together. We're applying our same Ohm's law rules. The chemistry inside has changed some. We still use what are called lead acid batteries in the car. That's all cars still have a lead acid battery, even if it's a hybrid vehicle. The exception would be electric vehicles do not normally have a lead acid battery, although they may. But full electric vehicles generally may not, but many of them do. And the reason for that is because it smooths out the voltage for the low voltage system. So they still use a 12-volt battery. So since the battery is the heart of the system, therefore other components can test bad if the batteries are not performing properly. So one of the mistakes people make is they think if their car starts, their battery's good. Wrong answer. A battery can be bad and still allow a car to start, and still have other systems that don't work correctly because the battery's bad. So the battery is used, it's only used to supply power during times when the engine isn't running or when it's starting. However, if the battery is bad, it can cause the voltage regulator not to function properly and not properly control alternator output. So one example I might have is I might be overcharging or undercharging. Undercharging is very common because of a bad battery, but overcharging also happens. Another thing that happens with a bad battery is I might have a radio that loses its presets. I might have a car that I take in for smog and the monitors aren't complete, but I haven't disconnected the battery. I haven't had anyone work on it, but my monitors aren't complete, so I don't pass smog. Because what happens is once my battery voltage gets down below about 9.6 volts, computers start forgetting things. So even though my car may still start, it's not going to necessarily, it might wipe the memory on some of the computers. And when we get in European vehicles, that's even more sensitive because some of them have problems under 11 volts. So, very, very voltage sensitive. So my car might start, might have other issues. Also, even if my battery voltage isn't going low, my charging system is only going to put as much in the battery as it says it wants. So what if my battery says it's not hungry? It doesn't want any amps, but yet it's only 50% full or 25% full. But it keeps telling the charging system, no, I'm good. Now the charging system's not going to charge up the battery correctly. It's not going to have enough current available possibly for other loads. On the other hand, my battery could be bad and saying, I'm really, really hungry. You've been eating all day and you haven't done anything. Yeah, but I'm really hungry. And the charging system is going to keep pumping stuff in and cause it to overheat or boil over or other issues. So the battery is the first thing we test. If I suspect any kind of starting or charging problem, if I have any kind of computer problem, I want to make sure the battery tests good. especially if it's a weird computer problem or intermittent problem, just to eliminate, make sure it's not a problem. And this problem is exacerbated by being in Southern California. Because in Southern California, I can drive around with a bad battery for 6 months, a year, on a battery that's bad. Why? Because it doesn't get hot here and it doesn't get cold here. The days that we see a lot of battery sales, or the weeks we see a lot of battery sales, is the first cold spell of the year. First time it gets really cold, like the 30s. And the first time it gets really hot. You know, it's hitting 100 or hitting the high 90s. That's when we see people need batteries, because those are the days their cars don't start. Reality, those batteries have probably been bad for quite some time. So because of our mild climate, customers are not really thinking about their battery. They're driving around with batteries that are bad. So we see other issues because of those bad batteries, that if I lived in Wisconsin or Pennsylvania, I would be getting snow in the winter, hot in the summer, all these other things. Batteries wouldn't be making it. It would not be as big of an issue, because cars would be failing to start because the batteries are bad. So when we look at batteries are more than just their 12 volts. We really need to look at them from a standpoint of a couple issues. One is their cold cranking amps. So cold cranking amps is the amperage that a battery can deliver for 30 seconds at 0 degrees Fahrenheit while maintaining a terminal voltage of 7.2 volts or 1.2 volts per cell. So wait a minute, didn't I tell you that things start like falling to sleep and not working under 9.6 volts? And yet we're rating batteries down to 7.2 volts, almost 2.5 volts less than I'm allowed to have as a minimum. So cold cranking amps is important, because that's what the power I need in order to be able to really crank over that car in adverse weather conditions. So a high cold cranking amp battery is going to have more power to crank my engine over, which is going to be exponentially more important the colder it gets. So again, here in Southern California, we really don't experience that. But gee, if I go skiing for the weekend up at Big Bear, up at Mammoth, where now it actually gets cold, it's amazing how many people tell me my battery was fine and then I went skiing and it went bad when I went skiing. No, your battery was bad before it left. Just no one tested it. Or if they did test it, you didn't believe them. Most places, when they do a lubrication service, an oil change, test the battery. The reason for that is they know that batteries will test bad and be bad before they get the customer stuck. And the idea is to replace it before you get stuck somewhere. Because reliability, most customers want reliability. And so that is really what we're looking at when we test the vehicle. Because the concept when we service a vehicle in the shop to do an oil change, preventive maintenance, is we don't want that customer to have anything happen to their car. And we want to see them back when we told them to come back based on mileage and based on the type of vehicle they have and what their mileage interval is between service. So we don't want the customer to have any problems. So anything we see that we think might be a problem, we're going to advise the customer of it at this time, whether it's tires, battery, cooling system, leaks, any of those things. Because we want that customer to be able to drive that next 3,000, 5,000, whatever thousand miles and not think about, is my car going to break down? And then the customer comes in and we do a service and look at the car again. And most customers, that's what they want. Some customers get really upset because, I took it for an oil change and they told me I needed all this stuff. Well, unfortunately, sometimes people are overly aggressive and say people need things they don't need. Other times they don't explain what the need is. Is the need a preventive maintenance? In other words, is this going to help your car go 200,000 miles instead of 100,000 miles? You're not going to notice a difference whether you do it this week, but you're going to notice a difference if you're going to keep the car. Is this something that we noticed is bad, that if you don't fix it, it's going to make other things bad and get worse and cost you more later, but it's not going to cause you to walk? Because the misconception people have is that if they don't get the things fixed that are recommended and they drive their car and it doesn't break down, that the shop was lying to them. And many times that's not the case at all. The case is the stuff that's being recommended is we're looking down the road, trying to prevent the customer from having issues. And cars can drive with a lot of issues before they eventually need a tow truck. So that's why it's important to have that conversation. If someone's doing repairs on your car, doing work on your car, is really understand what they're trying to explain and what they're trying to say to you, and make sure that shop is referable. And most shops are. So my battery, yes.
So we can start the car at 7.2 volts, and below that we can no longer start the car.
Yeah, you could. No, once you get below 9.6, the car won't normally start. But what we're doing here is we're testing the batteries. So in order to test batteries, I need to have a standard scale, and we use a couple of them depending on what I'm testing it for. One of them is this cold cranking amp test. So this test is done at 0 degrees, and they're going to see how many amps it can deliver for 30 seconds and keep the voltage at 7.2 volts or higher. And actually, they pull it down to 7.2 to measure how many amps. So this is really a stress test. It's not a real world thing. We're not going to see that 7.2 volts when we're starting the car. But if we're going to baseline something, if I'm going to compare the battery I get from Interstate to the one I can get at Sears or the one I can get at Pep Boys or Napa or Firestone, I need to have some scales that I can compare, A to B to see are they the same thing? Am I buying the same thing? Because it's more than just price. Obviously, price is going to be different. But also with the price change, what else is changing? So this is one of those scales that allows me to kind of look past the marketing hype and let's look at the nuts and bolts of the battery. Let's look at what I'm actually buying. And so that's where I start this off with. Before we get into construction, let's talk about the parts of the battery we're actually buying. So one of the parts on battery, we know they're all 12 volts. One of the parts I'm buying is its CCA rating. What's the cold cranking amps, right? So what's the strength of the battery? And this is measured at 0 degrees. Another thing I'm going to look at is my reserve capacity. So reserve capacity, often shown as amp hour rating, although it can also be shown as RC. Simply put, it's the number of hours that a battery will last with a 1 amp drain and still maintain voltage above 0. Well, think about it. I already told you anything below 9.6 ain't helping us. This test is how long it will take to get to 0. So again, we have a benchmark test that's not, my battery is dead a long time before it gets to 0 volts. I can't do anything with it. But this is a benchmark test that allows me to compare battery A to battery B to battery C. So some manufacturers require a lot of reserve capacity, 125 amp hours. Other manufacturers might only require 60 or 80 amp hours. And this depends on how many accessories the car has. How many things are drawing power out of the vehicle when the key's off? How long do we expect our vehicle to be able to stay parked in one place and no one go out and start it and have the car still start? So based on these decisions, manufacturers have a recommendation for how many amp hours the battery should have. So I could have a battery with really high cold cranking amps, but lower amp hours. I could also have a battery with lower cold cranking amps, but very high amp hours, or I could have a battery with high cold cranking amps and high amp hours. So it really is important we understand what the manufacturer of our vehicle wants from a battery and what they're trying to do with it. So this is another rating that we have. So as we look at these ratings are actually stamped on top of a battery. So in this case, I have a battery. It happens to be an Interstate, it's an MT58. The 58 stands for the group size. And I got a graph coming up on group size we'll look at on Monday. But the group size means that a group size 58 is a group size 58 is a group size 58. No matter who is selling it to me, that battery is going to be the same height, width, depth. It's going to have the same little tabs on it I need for mounting. The case on it is going to be identical because it's made to those specifications. I have 540 cold cranking amps, but I have this new number, 675 cranking amps. Well, cranking amps is measured at 32 degrees. And in the 1980s, when we started seeing DIY auto parts come out, they started selling batteries, and they saw this new thing where they would advertise their cranking amps. Well, as you can see, cranking amps is higher than cold cranking amps. So now they are selling a less expensive battery with a bigger number, 2 different scales, very deceptive. So some batteries still only show cranking amps. Some batteries will show cold cranking and cranking like we do see here on Interstate. So you have both scales to measure. Some batteries only show cold cranking amps, but it's important to understand that the CCA and CA, 2 different test scales, are going to get 2 different numbers. And then we see my reserve capacity in this case of 80 amp hours. So these are the numbers we're looking at on batteries when we ID a battery and see, hey, what's the group size? What's the capacity? And then compare that to what my manufacturer says I need for my car. So this is a good stopping point for today. I want to at least tickle batteries a little bit. We're going to get in, and then we're going to start off with looking at how temperature affects battery performance, and then actually get into battery construction. We're going to get into hybrid battery construction and so on. So I am going to turn on a quiz. I think I already have it set to come on. It comes on at 10 o'clock today. It's due end of day Monday. And it is just a PowerPoint review quiz. So all the questions I asked you in the last PowerPoint, the questions are there, the ones that translated well. The questions are there, and it's a multiple guess answer. So if you took notes or remember what we talked about during the PowerPoint, you've already got all the answers. Just go through and take that done. And even though I already gave you all the answers, I still give you 2 chances on the quiz. So how good is that? I try to make it happy. If you notice on the quizzes have 2 different point values normally. Some quizzes, the questions are worth 1 point each. Some quizzes, the questions are worth 4 or 5 points each, normally 4. If the questions are worth 1 point each, those are questions I've already given you the answers to. Those are review questions. If the questions are 4 points each, or I think I have one quiz that are 5 points each, these are questions you've never seen before. So that's a good way of kind of looking at how many questions in the quiz. If they're 1 point each, we've already gone over it. That's a PowerPoint question. I've already given you the answer. If they're 4 points each, if it's a 4 point question, that's not something that I've given you that specific question before or that specific answer before, although I'm sure I've talked about it and I'm sure that we've covered it and all that stuff. So on that note, everyone have a great weekend. I will see you on Monday. I know, Chris, you had a question for me after class. Thanks, everybody.
Thank you, Mr.
Brian. Have a good one,
Thank you,
everyone.
Mr. Brian.
You bet.
Thank you, Mr. Brian.
Bye, guys.
Have a good weekend.
You too.
Thank you.
You bet. So what do we got going today, Christopher?
I was helping a buddy of mine with his AC. He swapped out his compressor, and we were trying to get, when he was trying to reintroduce the R134A, we couldn't get the compressor to kick on.
Okay.
We put up some wiring diagrams, and we tried to do some tests. And he was thinking that there should have been voltage all the time at the compressor, but I noticed in the schematic that there was a relay, and the relay turns on, the power that goes to the compressor. So we were wondering what energizes the relay.
That's a great question. So we got to go back to the wiring schematic. So what kind of car are we working on?
It's a 2008 Nissan Sentra.
Okay, it comes from the intelligent power distribution module, but let me pull it up.
So that was one thing that we did notice, because we put in the new compressor, and we couldn't introduce the R134A because the compressor wasn't kicking on, so it wasn't taking any.
Right, and you don't have a vacuum pump, so you didn't put it under vacuum like we would in a shop.
No, we did. We put it under vacuum and stuff like that. So we did that. We put it under. He rented it from like AutoZone and stuff.
If it's under vacuum, he should have been able to fill the system.
Yeah, I don't know. I don't know what was going on. We thought that the compressor had to kick on for it to do anything, but
no, you should be able to fill that. You should be able to fill most of the system without the compressor on if you put under vacuum. You said that's an Ultima or a Sentra?
It's a Sentra. It's I think it's a 2.0 base.
Got it. And I diagnosed one of these at the college recently before we went offline, so that's why I kind of remember it.
Yeah. We found something online that had I don't know if it was how he found it, but we found that the IPDM has a self-test thing that it runs on itself. So
Right, yeah, it's on the network. It's on the network. It'll set codes. It won't set a code for this normally. I mean, it will if it's bad. But let me pull it off. But if I remember correctly, this system, you have a climate control module, and it talks to the intelligent power distribution module, which has a relay in it. And then it goes down based on looking at data. It goes down and turns the AC compressor on, is my memory. And it has a pressure sensor, so if there's not enough of the, okay, so the engine control module, I knew that was in there also. Where is my compressor circuit?
Yeah, that was my question. So we found that IPDM has a self-test thing that you can enter the little thing, you turn the key, and then the wipers will go low, high, it'll test itself, the high beams will go low, high, the condenser fan goes on. It basically checks all the operations.
Right.
And we heard the audible click from the compressor actually engaging. So we know that it was controlling it on and off, like it had control, but I don't know what gives it control under normal conditions. Is it the button that you push? And then I also seen in the diagram that we were going over earlier, it said AC request. So does that button in the cabin just request AC, and then it has to look at data from sensors before it actually ultimately gives it permission? Is that how it works?
That's exactly how it works. So what we have here, and I'm going to share the screen here.
Because the next thing we were thinking is maybe it was a pressure sensor that didn't regulate enough.
Let's see, we're kind of guessing a little bit here. So it's really hard without a factory, I don't mean a factory level scan tool, but a scan tool that you're able to go in, whether it's a Snap-on or a TEL, something like that, where I can go to manufacturer specific. Because then what I can do, and I've done this on your Nissan, is you go in and you can talk to the climate control module and you push the button for AC request. And it goes to yes. Okay, so that is working. That signal, if I remember correctly, goes to the powertrain control module, and then the powertrain control module goes to here. So if you look here, here's my compressor.
Correct.
Here is my intelligent power distribution module, and here's my AC relay. AC relay gets power from fuse 42. The EC relay has an AC compressor signal here, and it controls the ground. And if you notice here, I have CAN high and CAN low. So that's my network that's coming out over here. And so my network goes to my combination meter, and it's also going to go to some other things. So if I scroll this here, it may not show it on this picture. Yes, it did. So my pink and blue here, that's my network, right? Pink and blue. Are you following my arrow, Christopher?
Yeah, no, I see it.
Okay, so my pink and blue, which is my network, 3 and 4. I scroll to here. Here's pink and blue, 3 and 4. And it splices here. So it goes 2 different places. So one place it goes is my body control module. Okay. And then the other place I'm going is up here to my engine control module. So, and here's my front air door control, which is here, which is part of the body control system. So my body control module is what sees the button. It's going to talk to my engine control module, because my engine control module is looking at my engine coolant temperature sensor and my refrigerant sensor. They both report to my engine control. So you may be able to get value from that on generic. May or may not. But I do know you have the generic scan tool. So the next step is go into the engine module. Does it see that you're asking the AC to be turned on? And you should have a PID, obviously for engine coolant temperature sensor, but also for your AC pressure sensor. Those should hopefully both be supported in generic. If they are, then you can see, do I have pressure? Because obviously if there's no pressure, we're not turning the thing on. And then you can also see, is this requesting the intelligent power distribution module to turn it on?
Got it.
So I can't see what's being said. And obviously if I'd have a code for a network issue if it wasn't talking at all. So I'm really not concerned with the language, but that's how the information is shared on here. And then, like you said, you use the self-tester that you were able to activate, and you heard the clutch go click, 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 click. So that means the wire should be good, because they have a real problem with this purple and white wire breaking on these Nissans right down by the compressor. So I've had quite a few of these where when I test it, the relay, we find out this wire's bad.
Yeah,
So I have had a couple of those.
He basically assumed that his clutch went out. He didn't really do any kind of diagnostics. So
He put a bunch of parts in trying to fix a problem, and he still has the same problem then.
Well, no, he has the compressor. He just bought the new compressor, but I thought of it once we were there. I'm like, well, hey, since I knew it just engaged the clutch, I'm like, well, we can hook up the old one and do the self-test again with it hooked up, and the clutch didn't go on. So the clutch did fail. The magnet did fail on the other one. We kind of got that from the test, but like I said, and the relay obviously has control of that side.
Yeah.
I'm just trying to wonder why when we turn the blower, the motor, the fan on high, and then push the AC max button on with the engine running, and the clutch just wouldn't engage. So we were trying to figure out what could possibly be. Right.
And it could be you got a bad pressure switch, or you don't have enough pressure in there. What concerns me, were you able to put any refrigerant in at all?
I don't think so. I don't think you would.
Well, if you couldn't get any refrigerant in, you're still under vacuum, your pressure switch would be reading correctly. You should have been able to fill that thing at probably 80 to 90% at ambient, just out of the 134A, filling it through with the engine off once you put it under vacuum. So I'm wondering if you had a Schrader valve stick, if the adapter you guys were using didn't work right. I've seen all of those things happen. But your pressure switch, if that's a supported PID on your scan tool, that's a great place to start. And we can see it's what? And you can see what? It's a 3-wire connector. So what does that mean? Power, ground, signal return. It probably uses 5 volts as a VREF, but who knows? But you're going to have a ground, a voltage reference, and a signal out. So for that matter, you could what? Fool it. Right? Couldn't we run through a resistor or run some other voltage back on the signal out so that you throw a resistor in there, so you now get, 4 volts out, 5 volts out. Now what does it think? Certainly at 2.5 volts, it should turn the compressor on. At too high a voltage, it might not. But just unplugging it, what does your data read? Because unplugging it should go to 5 volts. That may let it come on, but it probably won't. Because it's probably not going to come on if you're down close to 0 or too close to 5. It probably wants to see something in the middle. But again, and that's probably fairly easy to get to. But I'm almost positive it won't come on if it's unplugged. Maybe that got knocked off, unplugged, broken wire. Who knows?
All right, got it. That'll give me some things to do over the weekend.
Right. Well, now you know who's doing what, right? Right, you got the request from the body control. That's the push button switch. You got the engine that looks at it and goes, "Well, I don't know. Can you have AC? Do you have pressure? If my engine cooling temperature says we're below 0, where you're not getting AC. If I'm overheating, I'm at 250 degrees. You're not getting AC, right? Because we're not going to turn the AC on a car that's running too hot." And then, so I need to be in the normal range for my coolant temperature. And then you have pressure. Okay, now I'll ask the intelligent power distribution module, can you have AC to turn on the AC? Now it's its job to manually turn the relay on. And since it's doing it during the self-test, that tells me the wiring in the intelligent power distribution module and the network to the intelligent power distribution module are working. Otherwise, the control to turn it on wouldn't have worked.